Russ here from the Reg team. Our next speakers are Malware Analysis Specialist T. the Veox and Senior Consultant Jonas Eichinger. Their talk today is titled Analyzing Suspicious Artifacts, a Deep Dive. You'll have an opportunity to engage in a live Q&A discussion after the talk. A link will be displayed at the end of the talk, and clicking on the link will take you straight away to the live Q&A channel so you can interact with our speakers. Gentlemen, over to you.
All right, thank you, and welcome everyone. This is our talk, Analyzing Malicious Artifacts. There's a lot to dig into, so we're going to go through a few slides quickly in the beginning and then jump right into some demos. This is part one of at least a two, maybe three-part, four-part series. So let's go ahead and get started. So my name is Clay. I'm a manager in our CyberSOC at SRA, Security Risk Advisors, and I lead our cyber threat intelligence and our cyber threat analysis teams. I'm also a part of our internal SOC training development. And Jonas?
Hi, I'm Jonas Eichinger. I'm a senior consultant with Security Risk Advisors, or SRA, and I primarily work in the service lines of digital forensics as a lead investigator, as well as an analyst and engineer with the cyber threat analysis team. That's where we do a lot of our reverse engineering work, and then I contribute to the architecture and engineering group as well.
Awesome. So we're going to go over just a quick overview, a general approach, quick note about the tools we're going to be demoing, and get right into it. Why are we doing this? So we're digging into this to find out, like, what is the threat exactly, right? Pull out some IOCs and work towards improving our defensive and our learning capabilities. I made note on the side to the type of cyber threat intelligence that these items speak to. Another very important one is gaining intelligence into current threats. So this is strategic threat intelligence. And we're seeing more and more organizations starting to do this, which is great because really the best source of threat intelligence is internally sourced information. Could come from ongoing phishing attacks, forensics investigations, etc. And the general approach here, OPSEC is always critical, right? We don't want to tip our hand, show our hand to the attackers. So offline analysis and no public sandboxes. A good approach also is to prioritize analysis. What goals? Set some goals and work towards those. Those will help keep everyone focused and keep the investigation moving along. A few goals might be determining whether or not something is malicious. This talk has made the determination that it is malicious, and so we're going to dig into that further. What type of malware is this? We can track these findings and save them so we can do timeline analysis, right? Is this attack we've seen before? Can we associate this with a certain threat group? Have we seen these types of TTPs before? Those sorts of things. So those are some basic and maybe slightly more advanced goals that we can work towards. A general approach we're going to take here with the PE files, so portable executable files, going to focus on static analysis, and we'll do a little bit of dynamic analysis as well. But focusing on imports and exports, focusing on the Windows API. By doing this, we can perhaps hone in on some of the functionality and capabilities within the piece of malware that we're analyzing. And we'll go ahead and move on to shellcode.
All right, so the other type of malicious code that we're going to be looking at today is shellcode. Now, shellcode is really just a name for any sort of a payload of executable code that is going to try and be run in a network environment. So the name itself kind of comes from the fact that this type of code, this malicious code, is usually used as kind of a initial entryway to give an attacker remote shell access, hence the name shellcode. So really, even though that's not what won't be happening, it might not be opening up a reverse shell necessarily, that's kind of the lineage of the term shellcode. And if we look at shellcode from a technical perspective, right, we're looking at position-independent code. So the shellcode, when it gets executed, it can't always assume that it's going to be executed from the same block of memory. It's going to be injected at different times into different types of applications, and so they may be, and it's going to be, you know, kind of hard-coded for that instance. And so as a malware analyst, we have to figure out a base pointer and then dereference from that point on to be able to actually make sure that we can run that position-independent code during the analysis. So there are a couple of different tools that we're going to be taking a look at, and they all support the ability to kind of set those reference points.
Awesome. Some tools that we will be demoing are captured on this slide. If you have any questions, please reach out in the chat. We are going to kind of move through these demos quickly. We want to try to squeeze a lot in. So without any further ado, let's go ahead and get started. The first demo is going to actually be a nice sort of segue from the previous talk when we were looking at malicious documents. So it's going to start with a malicious document and pull out something interesting. Okay, so yeah, before we get into the demos, there is a certain amount of background knowledge that is expected for people to know. If you do have questions, don't hesitate to reach out, and we can point you and direct you to some useful resources. So for this demo, we are going to take a look at a Word document, and we're going to use OLE dump to do so. So I want to, the goal here actually, well, let's go ahead and just dig right in, using OLE dump on this sample. So I found a nice sample to use for this demonstration. There's quite a bit of VBA code included. That's what this uppercase M signifies. But there's also in capital O, this object pool here. So this is interesting. I want to find out what this is exactly. I'm assuming it might be an executable, right? So so let's look at OLE dump here. Let's see what the options are. Just a quick overview here. Okay, so yeah, we can do a hex dump. We can also do an ASCII dump, strings, and it can handle compression as well. So let's try a few of these out here. You know, the stream is 16. So let's just look at that. Okay, so that gives us a bunch of stuff. Looks okay. That looks like a Windows file path. I think we're on the right track here. Let's go ahead and do this decompress and just do the hex dump here and see what we get. Okay, so this is what we want, just a hex dump of that object that's embedded in the file. So let's save this. Sample2.hex. Okay, great. So I'm going to go ahead and open this just to take a look at it real quick. Yeah, great. All right, so while we're here, I'm going to go ahead and select all and do a copy. Now, there are different ways of doing this. For this demonstration, I'm going to use CyberChef here, running it locally on my Remnix machine. So I'm going to paste the hex here. Let me try this again. Select all, copy that out, paste. Okay, much better. Scroll up to the top here. All right, so from Hex, that's the recipe we want to apply. And doing so, it looks like, okay, so this is looking good. We see this program cannot be run in DOS mode. This is a good indicator that you're close to the beginning of a PE file, a Windows Portable Executable. And we see MZ, that's the beginning of a Windows PE file. Those are the magic bits there. So, and M, so we don't know, if you don't know where MZ is, you can just guess. Okay, take another chunk out. This will update. Okay, good, we're getting close. Awesome. All right, so now let's go ahead and save this. Just save it there, that's fine. All right, get this out of the way. And hopefully this will come through in the video. Let's go ahead and close this. Okay. All right, so we should have our file that is, okay, great. Looks like it's a DLL. Okay, so we're already learning some information about the object that was embedded in this Word document. So the basic process there was we used OLE dump to extract a file from a malicious Word document, and that we created a hex dump of that, dumped that into CyberChef to do and applied the from hex recipe, and that gave us a binary that we downloaded and saved. And what we're going to do next is I'm going to, in this demo, and I'm going to transfer the stuff over to a Windows machine, a Windows VM that is isolated and has a number of tools that are going to allow us to take a closer look and analyze different aspects of this sample here. All right, so that was the first demo. And again, if you have any questions, don't hesitate to reach out, and we'll go ahead and dive right into the second demo now. So we're going to look at a new sample here and go through a general process that I like to take. There are different, variations of this, but my general process is to open the binary. We're looking at this sample here. Using PE Bear, really like PE Bear a lot. You can use PE Studio as well, get a lot of the same information. But here, one of the first things I'll look for is this optional header. Under DLL characteristics, you'll see DLL can move. So this has to do with ASLR, the randomization of memory addresses when this thing runs. So it's randomized now. I went ahead and wanted to show you, compared it to when this is not set. So when this runs, the same memory addresses will be used. So how I did that here, so that's one first step that I did, or that I do. I use CFF Explorer, pop the binary in there, go to the optional header, you'll see DLL characteristics, click here, and you'll see DLL can move. If you unselect this, say OK, and then save it, then you'll get that, you'll have it set to where it's that's not set. So that's typically the first thing that I do when doing this initial static analysis. So from here, we can also look at imports, right? So we do see a few imports here. Looking at the kernel 32, we do see a number of Windows API functions that are imported. Whether they're used or not is another story. So let's go ahead and plop this into IDA here, IDA, the free version, and gonna go over here to imports. In here you can, I'm gonna focus in on virtual alloc. When a lot of DLL injection happens, and malware does that a lot. It's very common, and it uses virtual alloc or virtual alloc EX to accomplish that. So that's one of the first functions I normally look for. I also look for is debugger present. This is just an anti-analysis technique that a lot of malware authors use. And this can be implemented in a number of different ways. Sometimes you'll see the actual import of the function. Other times they sort of import the function in a more clever way and you don't see it. So those are much more difficult to catch. However, we do see it clearly here. So with these two functions we're going to focus on just for this example, because I know what's going to happen with this one. What we're going to try to do is see if we can't monitor this address space and see if anything interesting is dumped into it or loaded into it as it's executing. So to do that, we'll load the sample into X32 debug. Here we go. And I'll adjust the size of things for the video here and probably zoom in a little bit. So we're going to set a couple breakpoints. The first one we'll set for is debugger present. And we can see down here that yes, a breakpoint was set. And we'll set one on virtual alloc. Okay, great. Go over here to the breakpoints tab and see we have these set. So it'll also break on this entry point here. So we're going to go ahead and run this. And here we see is debugger present. So if you're not familiar with this Windows API function, you can search it up, look at their documentation, and find out that when this returns a 1, debugger is present. Otherwise, it'll return a 0. So if we sort of let this do its thing, keeping on EAX here on this register, we see that it's set to 1, and that's the value that's going to be returned. So we're going to patch this in place. We're going to modify this value and set it to 0, and hopefully we'll get past this anti-analysis technique. Looks good. So go ahead and play here. And here we're at virtual alloc. One of the last parameter here should be the address. That's going to be cleared and allocated. So we don't know when all of this is going to happen exactly. As you'll see in a minute, things can get a little bit more complicated. So go down here. We'll follow this in this dump here, just in case we catch it. See if this value changes. No. EBX, well, maybe they're using this value, right? So let's follow this in dump 2. So since we don't know for sure, I'm just casting a wide net, and hopefully one of these will find something interesting to get loaded into that space. So let's continue. This is running. Okay, it paused again at virtual alloc. So let's step through here. Get right before this jump. Let's check the dumps here. So far, nothing. So I don't think any of those worked. So let's try these values. Try this first one. Oh, cmd.exe, that looks interesting. Go over here, load EBX into the second one here, and we'll continue on. And this is something interesting we're showing you. ZW Allocate virtual memory. So this is a different API function. I would say it's a little bit closer to what's the word I'm looking for? It's a little bit like calling this function directly, where virtual alloc, I think, calls this function. So this is going a little bit lower level, basically. But you notice it's not calling it in the same way. And so I think this is just a technique that's used to sort of abstract that away and sort of hide it from us. Otherwise, um, you know, we didn't see this in the imports, essentially, so we didn't know that, oh, we could set a breakpoint at that function, perhaps. But now we could, right? If we wanted to go ahead and set a breakpoint, we can go ahead and do that. And we'll watch this value as well. So this is calling this. Let's go to a different dump here. And again, we don't know if this is correct or not. That looks familiar. Right, looks pretty similar. Address is close. Go to a new one. Keep going. Okay, not seeing anything cleared. So what we should see is this this dump should be zeroed out before anything is loaded into it. So we don't see that happening, so we're going to continue. And hopefully we'll see something get loaded. Maybe, maybe not. Oh, let's look at this value here. Let me go back to dump 5. This value here. We'll follow that in the dump. Okay, looks like it's still running. So I'm going to go ahead and, just in case I did this too late, I'm going to follow this in the memory map here. And I'm going to dump this to a file. And I'm hoping we get lucky here. Okay, that's still running. I'm not going to mess with that. But what I will do is just to come here. Okay, it's not empty, so there's something there. So let's, just to use a different tool here, let's use PE Studio and open this. Aha, it looks like we did get lucky here. Bunch of strings. Oh, interesting. Okay, cool. PowerShell 127.0.0.1 localhost. And here we see a download string. Okay, so this is interesting. So, awesome. So we saved this to a file. So what I'll go ahead and do is, so to summarize, what we've done is we used PE Bear to look at the imports, the optional header. We noticed that the DLL can move, that this was set. So we used CFF Explorer to disable that flag, to remove it, and then save that file. So ASLR is not set. Loaded that into IDA freeware, looking for some interesting APIs, Windows API functions that might be of interest to us, and set breakpoints on those within X32 debug, and sort of stepped through this and let her run a few times here. And then we noticed this address, which I'm assuming was set last by this allocate virtual memory. Looks like that's the memory address that was used to dump this, which could be a DLL, into memory. Inside that memory, it looks like there's, or inside that DLL, there's a reference to PowerShell, create token privilege, some interesting functions here. And what else can we see? Reference to some DLLs. Let's go back down. Oh, something base 64. I don't know. Keep going. See if there's anything else of interest here. And this is just sort of the process, right? We're not sure exactly what we'll find, but we're just taking a look, seeing if anything interesting stands out. Perhaps something more we can dig into. I've seen this before, and I'll show this in a demo coming up next, the same sort of pattern. Anything else of interest? Some reference to Kerberos. And again, just because you see it here doesn't mean it's actually being used. Okay, here's looks like a user agent string, perhaps. Okay, that could be interesting. If it's trying to download something or communicate with a C2. Okay. So, got some stuff that we could start to dig into here. I'll conclude this demo for now, but we do, and I'll stop this. We could dig into that more and do some more analysis, but we were able to pull out a DLL which looks like it might have a beacon inside, and executing PowerShell. Perhaps that PowerShell is might be attempting to download the next stage, perhaps. So we'll go ahead and conclude this demo here and see you on the next one. All right, so that was the second demo. Again, questions, drop them in the chat, and we'll get back to you. And on to the third. For this demo, we are going to be looking at a Cobalt strike beacon, and it's stageless. So I copied this hex out, converted it to a binary here, and now we can kind of start looking at it from an analyst's point of view. Opening it up in PE Bear here, you can look at a few things here. The general information, optional header, looks like the DLL can move, so ASLR is set. We can come in and look at the imports here, and we do see a bunch. Some particular ones of interest would be this virtual protect, create process, open process, even this create tool help 32 snapshot that can be used in creative ways. What else here? I think those are the big ones. Create pipe, that looks interesting. Virtual alloc again, load library. These are all signs of, the functions in particular that are signs of potentially a reflective DLL would be load library A, virtual alloc, and what else? Get process, get current process. Let's see if there are any others here. Yeah, so those three in combination kind of lead me to think that this could be a reflective DLL. You can look at exports, and yeah, here, reflective DLL says it right there for us. That's great. It's not always the case, but looking at shellcode, that typically, or that can be. We also see beacon.dll. So right off the bat, I know, just having been through this, and I know where the sample came from. This is a Cobalt Strike beacon, and it's pretty obvious with all of these indicators. Now, what's it doing exactly? Well, prize C2 traffic of some sort. So it's there, and it can, be used for that purpose. So what else can we dig into a little bit? There is CS debug. We can load it up in here. Say find shellcode. Said a few other things here, and let's just see what happens. Let's see what we get here. So without digging into it too much further, we were able to at least make that determination by looking at the properties that this is a Cobalt Strike beacon. So here's, we get some information back from SC debug. Not going to use any of that for this example, but you do see the PEB and some other information here for us that might be useful if we were going to perhaps dig into this further. But for now, for the sake of time, we'll end it there and get back to the talk. Thanks.
Okay, so in this demo, I'm going to take a look at a Cobalt Strike beacon. It's a staged beacon. I'm going to be taking a look at it with a couple of different tools. One is XXD, Hex Editor for the command line, and then two different emulators, Shellcode Debug and Speakeasy, and kind of compare and contrast the two running through the same sample.
All right, so to start out the shellcode demo, I'm going to go ahead and take a look at the files that I have to work with here. So we have a couple of examples. We have some Cobalt Strike staged and stageless beacons. Right now we're going to be looking at 32-bit code. A lot of the malware that I've seen in engagements before seem to be 32-bit at this point still. So we're going to be taking a deep dive into those 32-bit beacons, and then we also have a set of interpreter reverse shells as well. So we're going to take a look at both those here. First, I'm going to run XXD to just get a hex value look at these shell codes that I have. So let's look at the stage file first. So this is nice. You can already begin to identify certain bits and pieces. In the shell code, for instance, we have here something that looks like a user agent string and an IP address. This is a quick way, if you have access to shellcode, you can obviously take a look at the just the hex value view and then the ASCII decoding of it, and you can already tell a lot about shellcode from that. However, I want to go ahead and run this through scdebug. So I'm going to run scdebug scdb gc, so the console version, -f for the file. We'll begin with looking at the stage beacon. And I'm going to run a couple of other parameters. I'm going to run -s, which is going to allow me to set how many steps the emulator should actually step through. So how many instructions it should step through for this shellcode. I found 10 million to be usually sufficient for most shellcode beacons that are staged. So this makes it basically stop the emulation after 10,000 steps. and that usually gives it enough time to get through most of the shellcode payload, at least the first initial stage part. Obviously, it can't reach out to the internet because this is offline, so it's not going to be able to pull down that next stage, and the C2 is not up. So that's das-esh, and then -r is going to give us a report at the end as well. So we're going to run that. There we go. Okay, sorry, missed the 0. But as we can see, was able to load up the shellcode, loads up the WinINet API, and then makes a connection out to this IP address, which is the C2 callback that was set up for this beacon on port 80. You have the actual path that it's going to try and pull something the next stage from. We have the user agent that the beacon is going to use for that internet callback. You can see that it's also allocating memory for the next portion from the internet callback, right? So we have the internet read file for that buffer of 60,000 bytes, which was allocated here. But obviously it's because there's no active C2, it's not going to be able to download anything, so it just kind of stops here. And then we run out of our step counts and it ends the analysis. So we can see that it reads, it does a DLL memory read that was detected. We have a signature found for the hash or harmony. And yeah, that is what we can see with the shellbug debug utility. And then I also want to give a run this through another tool that I've been using more recently, which is Speakeasy, which is another malware emulator brought up by the folks at FireEye Mandiant. So Speakeasy runs on the Unicorn emulation engine and in QEMU, and then it has a Python backend for interacting with it. So to run Speakeasy, we're going to run _speakeasy.py, and we're just going to load our file as well. That, and I think here the parameters are going to run our -r-a architecture x86. All right, so similar concept here. Again, we're seeing the kernel loading this library, the WinINet library here. We have the connection being opened. Here we have the actual IP address. The port, which was featured in the previous, in the shellbug debug port 80 here, it's not, I guess, humanly, it's not in a human visible form here, but this 0x50, that is hex for 80. So we do get that information there as well. Same with the path that it's going to request. We do have these internet flags, which I don't believe are captured in the shellbug debug and the shellcode debug tool. And then again, here we have the actual HTTP requests using the WinINet library with the user agent as well. And then again here, the internet read file, where it's going to try and read that memory from the internet address, and then it catches a unhandled interrupt. Obviously, you can't get that file from the C2 server, and so it finishes the emulation. So both really good tools, I think, in my opinion, for quick analysis of shellcode. Shellcode debug has been around for a while. I think it's nice from a single user perspective, but I think that Speakeasy does seem to run quite a bit faster, and I think has some more capabilities to be automated as well. Using it has a container as well that it can deploy each analysis into. So you could possibly look at scaling this to a whole enterprise scale. So really two great tools to look at for shellcode analysis of malware.
All right, so that was it for all of our demos and our talk. We really just want to say a special thank you to Dan Astor for creating some of the shellcode that we took a look at today. So thanks, Dan, for making that for us. We just want to say thank you to CactusCon for having us and for putting on this awesome conference for everyone. Just thank you to you for everyone who was able to come out and watch our talk and chat with us on the Discord. Thanks you for being here. We're gonna be here. Clay and I are gonna be in the Discord for a while and just answer any questions if you want to talk about any of the tools that we were able to demo. Just hit us up on Discord. And thank you so much.
Yeah, thank you, everyone. Appreciate it.
See ya.